Kia ora tātou. In this video we'll look at how surface area affects the rate of a reaction. So let's just describe what is meant by surface area. So if we had a substance that was a solid, and the substance shape was square, we're just going to do this in a 2D kind of dimension, and let's say in this square of the substance we would have 20 particles. So often when we're talking about a solid and rates of reaction, this would be magnesium. So let's just say this is a strip of magnesium metal. Now let's have a look at this and see which ones are exposed to the outside area. So if this was a strip of magnesium metal and we put it into a beaker and there were hydrogen ions on the outside just waiting to react with it, how many of these 20 particles could those hydrogen ions react with? So there is this one, let's colour them in, this one, this one, this one, just going through. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 14 particles exposed or that could immediately react with any hydrogen ions that are surrounding the magnesium. So what if we then, instead of having this shape, this kind of square shape, if we turned this into more of a rectangle? If it will let me, yes. Sorry, let's try this again. Like this, and so we'll go 10 across. 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 6, 7, 8, 9, 10. So as you can see, there's no particles here. That every single one of them is exposed to the outside of the magnesium. So here we've got 20 particles. 20 particles that are immediately, is what we'd say, immediately available to react. So this is the terminology that we need to use in an exam when we're explaining how the as you increase the surface area, the rate of a reaction would increase. So this one here is going to react faster than this one here, even though they both have in total 20 particles. So let's have a look at a past exam question. I think that's the best way to go through it, because a lot of this is not just understanding the concept, but understanding how you actually need to express that in the answer, which, you know, for better or for worse is what it is. So we've got question 1, cleaned magnesium ribbon reacts with a solution of hydrochloric acid. The reaction is represented by this equation. The reaction is monitored by measuring the volume of hydrogen gas produced over a given period of time. This is shown in the graph below. So compare and contrast the reactions of 0.5 grams of magnesium ribbon with 50 ml of hydrochloric acid and 0.5 grams of magnesium powder. So we can see here we've got the same mass of magnesium in both cases, but in this one we've got magnesium ribbon, and this one we've got magnesium powder. So the powder is going to have a greater surface area, and therefore a larger number of particles are immediately available to collide. So because there's more of them that are immediately available to collide, and this is where we need to link it back to that initial video where we're talking about the frequency of successful collisions. So we're going to say this means that there will be a higher frequency of successful, or you could say effective, collisions, and then so the rate of reaction is higher. So it's really just going through the motions. You need to be able to say each part of it to be able to get to a merit or excellence answer. and then we would have the magnesium ribbon, and we're basically just going to say the complete opposite. So we'd say it's got a lower surface area, less particles immediately available to collide, there will be a lower frequency of successful or effective collisions, so a lower rate of reaction. So let's have a look at how we would structure that into an answer. So, man, my voice letting me down. So in the reaction of hydrochloric acid with magnesium ribbon and magnesium powder, both form the same products. Got that there. However, since magnesium powder has a larger surface area, the powder will have more magnesium particles immediately available to collide. There will be more effective collisions per second. So that per second is the same as saying there will be a greater frequency of effective collisions. So you can either say per second or frequency. We didn't include that. I'm not sure how important that is for an excellence part. And then resulting in a faster rate of reaction. And then the magnesium ribbon, fewer particles immediately available to collide, slower rate of reaction. Both reactions will eventually produce the same volume of hydrogen gas as the same amounts of each reactant are used. So if we were to show this on this graph here, the amount of like if this was the powder, this is a terrible line here, but we're going to go faster. The rate of reaction is faster initially, but then it'll peter out to the same. This is supposed to be at the same point because we can't actually react any more magnesium. In fact, if there was like 1 gram of magnesium ribbon, then that would go slow at the beginning, but then we would end up with twice as much of the products. So because we're starting off with the same amount of reactants, we're going to end up with the same amount of products. So that's another thing that you can add at the end of your answer as well, which is often important. So thanks very much. In the next video, we will be looking at concentration and how that affects surface area rate of reaction. Thank you. See you.